Okay, so what I'm going to do now is I'm just going to kind of recap what we discussed and kind of learned in chapter 18. So the first thing we learned was that we discussed sample populations that followed a normal model. There was two different types of populations you could have. You could have a proportion, which dealt with categorical, and then there was a mean, which dealt with quantitative. And based on whatever group you had, you would have to use the different standard deviation formula to calculate the different standard deviations. So we calculated a standard deviation based on the sample. And what we learned was that the larger the sample, the smaller the standard deviation was. And then the next thing we did was we took time just to draw the curves and explain that according to the normal model, 95% of people would be between here and here, whatever the problem was talking about. And we would just explain it based on what we had done in the past. So what's going on with chapter 19? Okay, so for 19, we're going to find out what it actually does tell us and what we can actually state without making assumptions or without leaving stuff out. We can actually say what it is. Okay. We're going to be able to determine what the margin of error is. And we're also going to be able to determine our sample size needed to obtain a certain margin of error. So if I'm only wanting a 2% margin of error, we're going to be able to figure out what our sample size has to be in order to get that. So the best way I wanted to do this was just start with a problem. So your local newspaper polls a random sample of 330 voters, finding 144 who say they will vote yes on the upcoming school budget. So what can we say and not say about this? Well, before we can do anything, we have to calculate the mean and standard deviation. So the mean is 0.436, and then the standard deviation is 0.027. And so that's saying, on average, according to our sample, 43.6% of the time people voted yes, okay, based on that. Now let's see what we can actually say and not say. The first are going to be things we can't say. 43.6% of all voters will vote yes. Well, we can't say that because not all voters are like that. Our sample voted like that. And if you took another sample, most likely you would get a different sample proportion. Another thing we can't say is that it is probably true that 43.6% of all voters will vote yes on the upcoming budget. Again, pretty sure we're not going to get that exact percent again. It may be near that, but it's not going to be that exact percent. So we can't say that we're going to get that on the upcoming budget. We also can't say that 95% of the voters will vote yes between there. We think it's somewhere in there, but we're not exactly sure. The way we got those numbers was we took the mean, and we added and subtracted the standard deviation. Actually, two standard deviations. And so I forgot to put the 2 there, right there. But again, we don't know if it's centered around our mean. If our mean is 43.6%, then that's true. But if it's not, then we can't say it. This is actually what we're learning, what we can say, and what this 95% tells us. We are 95% confident that the proportion of voters that will vote yes on the budget is between 38.2 and 49%. This is what that 95% is important. This is why we do it. This is called a confidence interval. We know that we're 95% confident that the voters yes will be between 38.2 and 49. Okay, so the way you calculate the confidence interval, it's really just your mean plus or minus 2 standard deviations for that mean. The confidence interval is also known as the 1 proportion z interval. And once you calculate it, you can have a statement that says we are 95% confident that between the lower percent and the higher percent, blah, 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 just depending on what your situation is. But again, you have to say that it's 95% confident that will happen. It's not 95% of the time it will happen. It's not 95% of the answers will be in between there. We are 95% confident that will happen, and that's what a confidence interval is. One thing that we are going to start doing is that we're actually going to start using 1.96 because it's actually the most accurate answer. In the past, we've been using 2 just because it was easier to remember. But now that we understand the concepts, when we're trying to figure out our 95%, we're going to use 1.96. So the margin of error is just the extent of the interval on either side of the mean, the expected mean, or the sample mean, depending on whatever it is, the middle one, sorry. Our margin of error for our school budget was just 2.7. And really, because that's all it is, we go to the left 2.7 or we go to the right 2.7. So margin of error is very similar, if not the same, as standard deviation. So when you're dealing with confidence interval, there's some conditions. The first condition you have to check is the plausible independence condition. The plausible independence condition is just something that we kind of think about, and is there any reason to believe that they affect each other, that one event affects another one or one outcome affects another one? Usually that's not going to happen, but we just have to state whether or not we think things are independent. The next condition, again, random. Is everything random? 10% condition, are we less than 10% of the whole population? And is our success failure, so is our NP greater than or equal to 10 and our NQ greater than or equal to 10? So the last 3 are all conditions that we've checked before. Now we have to check something called the plausible independence. And again, that's just, is it likely that these things affect each other or don't affect each other? Okay, so what we're going to do now is I'm just going to kind of go over some examples, and hopefully that will help you clear up some stuff. So for example 1, it's going to have 3 different parts, maybe 4. We'll see how it goes. Consider each situation described on the next slides. Identify the population in the sample, explain what P and P hat represent, and tell whether the methods of this chapter can be used to create a confidence interval. Okay, so let's look at example 1. Okay, so please set up an auto checkpoint at which drivers are stopped and their cars inspected for safety problems. They find that 14 out of the 134 cars stopped have at least one safety violation. They want to estimate the percentage of all cars that may be unsafe. So the first thing we need to know is the population. The population is all cars in the world. The sample is 134 cars that they actually stopped. The P is the proportion of cars with safety problems. The P hat is a proportion of cars in the sample that actually have safety problems, and that is 10.4%. And the way we got that is just doing 14 divided by 134. Next thing we're going to need to do is check all our conditions. The first one is the plausible independence condition. Well, there's really no reason to believe that the safety problems of cars are related to each other. If one car has an issue, that doesn't really mean that the third or fourth car are going to have the same issue or a different issue. The next thing we got to do is we're going to have to say it's random. Well, the sample's not randomly, so hopefully what they did is they stopped cars randomly, and the cars stopped are representative of cars in the area. So that one's a little iffy. The 10% condition, 134 cars is definitely less than 10% of the entire population of cars. And then the success failure, well, when you multiply NP, you get 14, and when you do N times Q, you get 120. Both are greater than 10, so that's a good sample size. It's large enough. A 1P, a 1 proportion Z interval can be created for the proportion of all the cars in the area with the safety problems. So those conditions we can say have been met for that one.